Okay, welcome back everybody. We're going to finally break down step for step what this Gibbs sampler is doing. We're studying this problem right here. I'll just write out the posterior distribution for mu and phi, given all of the data, is proportional to phi to the n over 2 minus 1. That's the prior. E to the minus phi over 2 sum of the xi's minus mu squared. We sum over our n data points. So that's our posterior distribution. We've been using this to exemplify Gibbs sampling in Metropolis Hastings. We already worked our way through and understood what the marginal distributions were analytically, but we had no real hope of really understanding the joint distribution. And so imagine this in higher dimensional spaces. So more parameters in your model, I think it's those joint associations that you really want to understand. That's what I would say. So otherwise, why do you have them all tangled up with each other in your model? So you want to understand what their relationship to each other is. That's what I would say the end game of an analysis is. And then of course, is your model predictive? Do the parameters mean the right thing to you? So that would be kind of the holy grail, and maybe they would guide you into asking more questions and collecting more data. So rough outline of what I think science looks like. So let me just write down the Gibbs sampler that we're looking at. So this is going to be the sequential sampler where I'm breaking everything into Gibbs blocks. I believe the homework just asked you to code this thing up. T to some big number, big, until convergent. So anything that you're monitoring and you're reporting, it should be big enough so that the precision that you're reporting is accurate. Okay, so there's a lot of ways you can do that. You can impose lots of different types of convergence. So Cauchy convergence means if the sequence is getting tighter and tighter and tighter. So in the sense that the difference between the numbers that you're getting are something that you're monitoring. So I wouldn't be monitoring the output of the distribution because that's stochastic. That's always going to bounce around. So you're always going to have some gap there. But if I were computing the expectation or something like that, I might have, let the sampler run for 1,000 iterations after it's burned in, and then look at the next block of 1,000 iterations and see if those two expectations are close to each other. And I would probably be a little bit cautious, and I'd probably do it a couple times and see if those continue to be close to each other. Or you could do the pointwise thing where I run the sampler for some fixed number of iterations, I compute the expectation, and I do it again. And I do it again, and I do it again, and I compute those expectations after convergence, and I make sure there's a room within some tolerance. So that's why we like Monte Carlo, because it's a fixed amount of time you run for. If you run multiple chains or something like that and you get answers at the end of the day, you could do that in parallel and just launch everything, and everything takes the same amount of time. So if you're computationally rich, which I would say everybody in this room has access to supercomputers tomorrow. All you have to do is write a paragraph to ARC and they'll give you access. So this is a relatively easy process to implement, so long as you get the for loop right. Everything in the for loop. Correct me if I'm wrong. I think I say for your homework exercise, you're just going to sample this directly from the full conditional. Phi is going to come from its full conditional. So we're updating with the most current information. So I'm updating that first, so I need to initialize what phi0 is. So set that equal to some value, you pick it. We'll explore the behavior of starting far away from the truth. Last time when I just ran it for you, I started at the truth, and lo and behold, everything worked great. I think I asked you to just sample from these directly. That's a normal distribution. That's a gamma distribution. We worked through those in the first week or two. So no integrations required. It just had to do with recognizing the kernel of distributions and recognizing their parameters. Be cautious on this step. If you just go to MATLAB and R and assume their parameterization of beta, I think with over 50% chance you made a mistake. So for some reason, cosmic radiation makes us just do the wrong thing. You would think by random chance people would just get it right, but every time I go to it, I always encode the wrong one too. So I'm wrong more than 50% of the time with this. So I always check every single time because I hate chasing down that error. So this one's pretty straightforward, but keep in mind, they don't talk about this parameter, the precision. They talk about the variance. I actually do not care if you do this on the variance scale and you plug that in. You'd probably plug in 1 over phi for the variance right there. But if you want to do the whole analysis on variance, it'll work out the same. Just make sure when you're plotting the trace plot of everything, you flip over your variances when they come out of the sampler. No Jacobian required. They transform automatically.
Wait, that reminded me, were we going to talk about Q plots?
Oh, QQ plots.
QQ plots,
Yeah. Let's take a break in just a second and talk about what a QQ plot is. I asked you to just do this with the normal and the gamma, right? I don't ask you to build in the sequential, the Metropolis Hastings steps right here, right? If you don't know that, then I don't know if I can ask you anything meaningful. Okay, then I won't offer you extra credit. That's fine. So I was going to offer you some extra credit. If you guys are interested in it, we could address this conversation in like 1 second. Did I ask you to implement the Metropolis Hastings steps on the homework?
The first part of the problem, there's some sort of Metropolis Hastings, and then the second part is that make it simple. Yeah,
exactly. So the third part could be correct my code online for the proposal, and I point to it directly, and just send me the correction. I'll give you 5% class credit. So I'll repeat that if necessary. Okay. Got a midterm coming up, so something to do. If you want to ask me next week what I just said, I guess that could be fine. Okay. What we're going to do today is I'm going to assume I don't know how to sample from these, and I'm going to do MH steps on this. So Metropolis Hastings, where I propose and then I make a decision whether to accept or stay at the same location. What that'll give me the ability to do is slow down the sampler so we can monitor convergence and do all the things we're supposed to do. When you go to homework and you don't have MH steps buried in there, and you know how to sample from the distribution because you just call R gamma or rand n, depending on which software package or how you encode it, it'll converge almost instantly. So the full conditionals will just get you there, bam, in like 2 iterations. So I'm going to slow it down where I could use MH to speed things up a bit, but if I can speed things up, I can slow them down. So we'll just understand like the behavior of tuning and what we should monitor when we're looking at a MCMC output. QQ plots aside. Keep in mind, Wikipedia knows all about stuff like this. This is one of my 2 favorite plots. I learned about him a long time ago. So I love QQ plots, although they don't tell me everything, but they tell me a lot. So what do QQ plots do, real quickly? What's the goal?
Compare your references, or compare 2 distributions.
Compare 2 distributions. You couldn't have said that better. So I have 2 different distributions. So disk 1 and disk 2. I'll make one of them a histogram in a moment and talk about one as being a continuous distribution, the way most people use them, what the default setting is. But what you're going to do is you're going to make a plot. QQ. Does anybody know what these Q's stand for? They both stand for the same thing. Quantile, quantile. I've also heard of called PP plots. Does anybody know what the P stands for? Probability. So I learned that also, and I guess people like QQ. So I kind of like QQ too. It's cool. Quantiles. So what you do is you look maybe in the 5% quantile, so that's 5% of the distribution right there, and you get the, I would say, dist 1 Q1 value right here. That's this. So that's quantile, and I'll call that the 0.05 quantile for dist 1. And I do the same thing over here, where that's 5%. And I grab this value, I'll call it D2Q 0.05. And I plot that value right here. I'm going to call this DQ1, D1Q1, and I'll call this D2Q2. I probably should have made that notation a little bit more comprehensive. Too many twos, too many ones. So I'm going to plot that value, whatever it is. So those two different things. Now I'm going to do this at maybe the 10% level. So this would be 10% all the way over here. So that's the 10%. And I'm going to do the same corresponding thing here. I'm not going to give it any atrocious notation. I'll just talk about those points, and I'm going to plot those. So then I'm going to do the same thing for maybe the 15. That's not looking like 15, but you get my point. So, and I come up with the corresponding point, and I just do this all the way through everything. And if the distributions are the same, up to a shift in a scale transformation, this will be a straight line. So, those distributions are relatively similar to each other. So I will point out that if you do a location or scale transformation on the distributions, that will just tilt the intercept in the slope of that line. So it'll still be a straight line. So it basically tells you if they're equivalent up to location and scale transformations. So distributions that are different in the tail won't have a straight line, and I kind of love that about these. So distributions that look heavier tailed might look, so a lot of times they'll center everything and they'll make this line just the 45 line. They might standardize all of your data, and that would make it the 45 line. And then maybe it's like kind of straight in the middle. And the way I'm drawing it is you can dice this up a lot more than the 5% quantiles. For any data set you had, you could dice it up as many data points you have and have that fractional quantile. So you could do this a lot. So 5% is just a concept. But you might have straight lines right here, and then these might curve over at the end, telling you one of the distributions is heavier tailed than the other. So if you plotted a t against a normal, it would do something like that. And the lower the degrees of freedom of the t, the more it would inflect. So, and if you went all the way down to degrees of freedom 1, you got to have points way out here, and those would be those crazy points you get in a Cauchy relative to a normal. So those things people tell you to throw away in other classes, and I say, hold on to those. Those are the best part of the analysis. That's a QQ plot. So it's a way of comparing two different one-dimensional distributions. You could dice one of these up. This doesn't have to be a continuous distribution. You could compare an empirical distribution to a theoretical distribution. So if you just invoke QQ plot in a standard package like MATLAB or R, it'll assume you mean to compare it to the standard normal. And it'll take your empirical vector of data and compare it to a standard normal. So you could also hand it two vectors of data. You can take two continuous distributions and chop it up as finely as you like and hand it those vectors, and it'll plot this. What I really like about these plots versus like chi-squared test for telling us distributional fit. So you can bin up your data and do the chi-squared sort of thing if you know how to do that and compute a p-value And I actually don't have huge problems with that p-value because it's a one-sided p-value and it's just showing you discrepancy, so bigger means worse. I don't exactly know how to interpret that because it's really just, I have to do the Neyman Pearson thing if you know anything about it, and I can only calibrate error rates with it. So I know that. But I get it that in one-sided cases, the p-value might be a measure in some sense. We'll talk about this when we get into hypothesis testing. If that's over your head, that's my expectation. One thing that's not over your head is in one dimension, so I can do this marginally for comparing distributions, is I can see where the distribution is different. So if a test, a classical test tells me the two distributions are different because it has an exceedingly low p-value for its corresponding chi-squared type test. This tells me more. This tells me where it's different. So sometimes you could see like straight lines or something like that of data, but then there's like a blip in the middle or something like that. And I go, oh, that's really weird. So if they're different, the two different distributions, but they're mostly the same over here and here, although the variability is weird over here in that distribution, and there seems to be a dip in one of the distributions. There's probably some bimodality in one of those distributions, and I can start to see things like that, comparing the QQ plot, and go, what's going on here, you know? So if you're assuming something's normal, and you saw something like that, you're probably thinking, oh, it's a mixture of normals, probably. And over to the left-hand side, it has more variability, and over to the right-hand side, it has less variability. That's what I would glean out of the QQ plot. So I like that. It helped me teach me how to build my models. Question answered?
Absolutely.
Awesome. The next obvious question is, what's my other favorite type of plot? What's your favorite type of plot? You don't get QQ. That's mine. You guys have a favorite plot?
Box plot or histogram?
I like box plots. Histograms drive me crazy because I can't tell. So I'll take a QQ plot compared to a reference distribution any day over a histogram. So somebody the other day, just yesterday, was going, here's two histograms, they look about the same, and I'm like, my eye's not that good. So can you just QQ those two histograms for me, those two vectors? Oh, sure. Same conversation. Here's what it is. And yeah, they look pretty similar except here, in there. So let's talk about that for a bit. So histograms drive me crazy because of the binning problem. We don't know the bandwidth selection, and in high-D spaces, they're even more atrocious. I like them at first glance. I will look at histograms. Anyway, we could plot your grade distribution after Monday against a normal and see if we should curve your grades. I heard about that this week. You know, people asking for curving their grades. I was like, oh, so you want to go from a B to a C. So probably don't want to do the normal approximation. So I'm going to hypothesize that the distribution of grades in this class will not be normally distributed. They'll be very skewed, so to the right, and there'll probably be two modes. We'll see if that's true. We can plot against the QQ plot and see if we can see some of that. Or maybe you're right, the histogram would probably tell you just as much as you want to see. It's a pretty low sample. Okay, let's get into this right here. I want to just point out the Metropolis Hastings steps. Let me just fill these in before I run the code. So they would just break apart your block steps. What you do in the block sampler on your homework is just kind of do the exact same thing, your proposal, but you would end up, your proposal would be the product of those two independent proposals. And you'd only have one step. So this right here, what you might do is you might propose a mu star. I'm going to take this from some proposal distribution. I'm going to call this G mu given mu t minus 1. And let me just give you exactly what we've done in the code. So this is going to be centered at mu t minus 1. Oops, I got a t, so I've already blown my indexing scheme. So that's going to be a t here, just because I started it at t. And then I'm going to have, oh, yeah, exactly. So I'm going to center this here, and then I'm going to have some tuning variance, phi, and I'm going to leave that the same. This is a constant, and it's a tuning parameter. So what that's going to measure is how far from my previously accepted draw do I want to bounce around in space. I want to point out, unlike accept reject, we've got a proposal there too. The closer G looks like the target distribution, the better the algorithm is, and you can get that constant to be smaller, so your acceptance rate is higher. That is not the case here. This does not look anything like that. I would agree they're both normal, but what I'm kind of imagining is my target distribution's normal looks like that, where I'm going to be walking around the space with these little normals centered at where I was last time. And so I'm going to make some decision right over here. I'm not going to be centering the same normal on here. I would agree if I had an independent normal that I was always sampling from and not walking around the space, that would be the perfect thing to do. But if I knew that, I wouldn't be running a Gibbs sampler. I would know the answers. So we're pretending we don't know what the answer is, so we're trying to come up with a searching tool that searches out the algorithm, searches out the answer in a way where you're walking around the space and you're converging through this random walk. I want to point out an accept reject. If I were computing means of a distribution or something like that, if the number of accepted samples I accept gets bigger, my approximation gets closer. And that's all central limit theorem stuff. This is a random walk that is not independent, and the central limit theorem doesn't apply here. So we have a whole different branch of theory on why this works, and I'll present that to you later. So I'll give you the outlines of the proofs. I'll give you at least 50% of the proof, and I'll tell you what I'm leaving out, what I'm omitting, because I don't want to tell you everything there is I know about Markov chains. So, okay, so that's about what it looks like. So that's my proposal right there, G mu. I'm going to do something similar down here for phi. Anyway, I'm going to accept mu. So t plus 1. It's either going to be mu star, or it's going to be where I was last time. And this is going to happen with some probability. I'll call that alpha mu, and I'll tell you what alpha mu is in just a second. So alpha mu, so this is something you'd probably compute right in there, right before you make the decision. This is going to be the minimum of 1. And this is going to be pi mu star given x phi t. And this is going to be pi mu t comparing to where I was last time, given x, and conditional on this phi t term. So that was a constant in this block. When you're jointly updating it, both things will change. So you can compare convergence properties. It won't be too bad in either case. This is an easy enough problem with fast enough mixing properties that it almost doesn't matter how you do it, but I just want you to observe different strategies. So that's it. Did I make a mistake? Compare the ratio of the targets. All I have to do is write down the likelihood and the prior for that. So all I have to do is take that functional form, phi to the n over 2 minus 1, e to the minus phi over 2 times the sum of quadratics, and plug those things in. So I don't even have to work out what this conditional distribution is. I just work with the joint. So let me just write it down. really clearly. This is going to be phi t n over 2 minus 1. This appears down here too. I'm being rather superfluous. I probably would not code this up because I have immediate cancellation. E to the minus phi t over 2 sum of the xi's minus mu star squared e to the minus phi over t, phi t divided by 2 sum xi's minus mu t times, nope, that's it. That's all I would code up there. I wouldn't actually code that up. It scares me looking at it. So the e's frighten me. E's to this right here. Think about this. If my mu star, or where I was last time, let's think about this one. My initialization or something, my starting point when I'm burning in is very far from the xi's. That's going to be huge. That's going to be tiny. And I'm going to get all these division by 0 errors in my code, and it just will not converge. So what I would probably do is take the logarithm of all of this, and that'll be very nice. So quadratics aren't the problem. The exponentiation is the problem. And we've all heard this before, and it shocks me still to this day how fast exponentiation just kicks in. So we were all worried about this with COVID, the doubling period, and then it didn't happen. So it's hard to tell exponentiation sometimes at the beginning of a process. It starts looking like that. You can't tell until it's flying off. It's already too late. That's what people are worried about. And I would say rightfully so. That makes sense. So we'll examine the code. Where is my proposal? Don't I have inverse ratio of proposals? Isn't that supposed to be G mu t minus 1 given mu star compared to G mu star given mu t minus 1? And I guess I put some mu's on there. Shouldn't it be that?
Is it equal to 1?
It's equal to 1.
Metropolis.
Yeah. So think about what this distribution is right here. So this is whatever my tuning variance is. This is psi. I'll call it variance, so I'll put it here. E to the minus 1/2 mu star minus mu t squared over psi squared. So it's that distribution. So when I flip these arguments around, I'm flipping those arguments around. It's exactly the same distribution. So when I take this ratio where I'm just flipping those arguments, that thing is 1. So I wouldn't code it up. I wouldn't put it in there because it cancels to 1. Save myself another numerical heading. So I don't like multiplying by bizarre forms of 1. I just leave it out. I don't like adding bizarre forms of 0. On the chalkboard, it's fine, but on your code, not a great idea. If you don't believe me, do it. So I've done things like that too, just to find out it's a terrible idea. So anyway, that's that. And then here I do something really similar. And the only question is what is G phi given where I was last time? Oh, I see what the problem is right here. Let me call this plus 1 right there, and then at least I think I'm okay. So I messed up my indexing just slightly. I'm updating that one. So we'll update that one. I'm a little off right here. This should have been a plus 1 in here. This should have been a plus 1. Apologies for my indexing error. Do not try to code this up. Correct the indices. I know. So now I've got the mu t right here. So I gotta update that one. So this was mu t plus 1 right here, phi t plus 1. I have this and I need to correct all my indices. Oh, this one is phi t now. Phi t plus 1.
And should the phi should be the phi 0, so should it be phi t minus 1?
Yeah, it should have been, but then I've scrambled these all up. So this is the exercise. This was done intentionally. Fix it. We could fix it. You get the point. So I'm gonna erase it because I'm embarrassed. But it would take us more time to fix than it's worth. And you guys are all experts. So this is about when you code up minus the indexing errors. Update the mu, update the phi, keep track of it accordingly. Okay. Let's go, let's see this thing run in action. Big question is what is this thing right here? I should have finished writing this. Phi, this is gonna be phi t. I'll put it like that. So you can put a little phi here. I'll point out that in my code, I used it in a random walk normal, and that is an error. It's almost an undetectable error. Where can you read about that error? Yeah, Darren Wilkinson's blog, there's a link to it on the web page, so go and look at it. It discusses this error, and it shows how to fix it with a truncated normal. So in a truncated normal, you have to renormalize that thing, but you know how to do it using the CDF function. So the little erf function. So you can encode that and take the difference of two erfs and take the ratio of those. Turns out they're really close to 1 usually when you take that ratio. And he discusses that, and then he shows you a different implementation where he reparameterizes this in terms of the log phi, that is Jacobian up front. So that instead of talking about phi, you're talking about log of that parameter. So e to the log phi is still phi, so I can talk about log phi, but log phi, call that psi. You need to take a Jacobian to reparameterize that thing. But once you do that and encode it properly, now you can use the local random walk on that because it's an unbounded space between negative infinity and infinity. And he talks about minor issues with that. So please read through that. If you send me the correction that you're using in an email, I will add it to a folder, and I'll see that you've got 5% extra credit come the end of the class. So if you need some extra credit, just address this, be really clear about it. I asked you to do it on homework, but just do it again, see if you can get this code to run properly, and if you do that, just send me a note that you did it. With the correction, I don't need to see your whole code, just snippet that box. Send it to me, and give you 5%. That error is intentional. Okay, let's look at the code just real quickly. I'll tell you about some of the features of this code a little bit later. Some of it I don't want to address right now. Okay, I think that's pretty good. So I've got this code. It's going to hand me back mu's and phi's samples from this iterative process with Metropolis Hastings steps. How I slow it down or speed it up is through that parameter. So I basically just make that small and it can only tippy-toe through space. So this is the most unadventurous explorer. So implementation that we'll start with. Trace is just some functionality control. It just tells me I want to see all the plots as I go. Plotting as you go is probably the slowest thing you can do on a computer. So I will give you another just tidbit from my archive, is if you're plotting as you go, clear the figure as you go as well. Otherwise, you'll wonder where all your memory is going. But even if you're plotting the same points on top of each other, your graphic will know that, and you won't be able to see it. And all of a sudden, your memory will go out of control. I've chased that error a couple times in my life. Usually, all my plotting control, I just turn on and off with the toggle. Thinning is an interesting thing. It just says, instead of taking every sample and storing it, I could take, if I put in 2 here, it would let me take every other sample. If I plug in 10, it would store every 10th sample. So it's a sample from a sample. And a sample from a sample is a sample. So if I just take a systematic, like in an IID random set or something like that, taking every 10th number is still a sample.
Would you do that in order to decrease the dependence from one step to another?
You could do that. So some people will articulate this since it's a Markov chain that you're getting and maybe you want IID representations, is you can thin to get rid of the autocorrelation. So one way you could do this is you could take your samples with collecting everything and then look at the autocorrelation plot. So that's regressing every draw on every previous draw. That'd be the lag 1 autocorrelation. Or you could take every draw and regress it on every other draw, look at its correlation. So on and so forth. You could look at every draw and regress it on every 10th draw, look at its correlation. You don't even have to regress, just get the correlation between those. Do that for, you know, a large chunk of numbers, and where you see that autocorrelation fall off is that's how much dependence there is in the chain. So taking small steps also creates a lot of dependence in your chain. So it's not necessarily a great thing to do. Here's another thing you can do that theoretically sound. Instead of thinning, I could just shuffle the numbers at the end of the day. That works too. As long as I'm in the stationary distribution. As long as I'm sampling from that stationary distribution, the burn-in doesn't help me. Do not scramble that because you will not be able to tell what you're supposed to chop out. So only scramble after you burn the chain in. Otherwise, you won't know it's part of your distribution. So the reason people will thin also is for storage reasons. So back in the day, we would blow out our RAM like that. So nowadays, I'm like, I want to see your autocorrelations. You know, show it to me first, and if you want to make an efficient chain, then thin if you'd like. But it's just done for purposes of storage. So yeah, the answer, so there's no autocorrelation, I did all the things I'm supposed to. It's not a theoretical thing. You could just shuffle your answer and also break the dependence. Step size is part of my proposal variances, so I just scale everything to this, and I kind of can muck with both of them simultaneously. I have multipliers down below on the codes as well. Number of iterations, how long I want to run it for, the burn-in. Let's just not burn anything in. I'll just say no burn-in. My indexing, at least I have this one right, starts at 1. So I can initialize everything. Before I initialized everything at the truth, it worked really good. We saw that triangular shape. We'll see it again. I'd like to start it far away from the truth. These are the priors I'm using. I pad all the memory so it speeds up. I initialize everything, and then I go to town. Everything else in here is just plotting. So I plot as I go so we can see the trajectory of the samples. This is my random walk for mu, my proposed step. It's just this thing right here. So I propose out of rand n, I multiply by my step size. So step is actually my standard deviation, obviously, and not my variance. It doesn't matter what I call it. So it's some big number or some small number to me. And if I put in anything that's negative, I'll have problems in the code. So I make sure I don't do that. I get a new proposed value. And what I've done is I've gotten rid of all of the silly answer stuff in here. We'll look at it again. What I did just to be extra ridiculous is I wrote up this function and I took a log on the outside of it. So I computed trash and then I took a log of it to fix it. Just to make the point, it won't help you. So when I say do everything on the log scale, I don't mean take the product, you know, of everything. So I even worked in product form and I didn't take the sum up and upstairs. I took all my normal distributions in there and I worked through it in the worst possible way. I don't want to start like that, so I've simplified everything in terms of the log. So I have my proposed value, my current value, I store them separately. So I take the log of each one of these and later on I'll take the difference. I look at my ratio. This is actually a log ratio. I don't want to call it something different. But if I change to this other scale, I have to divide them. So if I uncomment those, I need to uncomment this. It's just to show you very bad numerical performance. On the chalkboard, it's exactly the same. Then I look at a log ratio, a log of a uniform. So if I change this, I also need to change that as well and not take the log downstairs. So if you do play around with this code, there's a few things you need to know about it. If you change this to the numerically unstable stuff, you need to change that and you need to remove that log right there. This would be akin to taking a uniform and seeing if it's less than alpha or something like that. This is this number right here, min. I never min with 1. Because if it's bigger than 1, I'm going to accept the value anyway. Any uniform I generate will duck it automatically. So it's kind of a waste of time, but doing the check is just as slow, you know? So I just compute this on a log scale. Since logs are monotonic, I can just take the log of the uniform and check if it's less than my log ratio. So more accurately, I should call this a log ratio. Plug that thing in. This is really just accept reject sampling in disguise. So if you want to know what you just did, but if I want to sample from a Bernoulli, here's an algorithm. So I'm sampling from a Bernoulli, let's say it's a Bernoulli 0.7, heads, tails, that paradigm. If the uniform is less than 0.7, I call it a heads. If the uniform is not less than 0.7, I call it a tail. And that's equivalent to flipping a coin with those corresponding probabilities. That is the inverse CDF sampling. You can just work that out, but it conceptually just kind of makes sense. So that's how I code it up. I never take the min. When we prove some stuff with this, if we prove detailed balance, we'll need to be aware that that is capped at 1. So the theory we would need to be aware of, but our implementation, whatever. I do the same thing down here. I also point out the proposal that I'm using is not symmetric. I'm using a truncated normal right here in the worst possible fashion. I just run a while loop until I get something positive out of everything. So it's fast enough, but that's the worst way to sample from truncated distributions. If that budges against 0 and all the mass is over to the left, this is a terrible sampler. That's always true. So sampling from high-dimensional truncated normals, like you would do in Albert and Gibbs' Probit model, is the hard part of that algorithm. There are some speed ups, but it still is the slow part. Same sort of thing down here. I work on the log scale. I don't give you 2 different possibilities and I update. So if you're going to correct something, I would like you to correct what my proposal is right here. So my acceptance probability isn't just the difference between these 2 things. It needs to be corrected by the ratio of differences in the CDFs of normals. So Darren Wilkinson tells you all about that. And then everything else is plotting. So let me just run it. See what we get. It's the exact same data that I had last time that I generated for you. True mu and true sigma, we'll see what they are. It's 0.25 for phi. So I think I picked the variance to be, sigma to be 2. So the variance was 4, so phi was 1/4, and 7 was mu. So exactly the same values. Let's run it, and we see a little bit different behavior than we saw last time. I started this chain very far away from the truth. This was my trajectory. I drew a line between the points, and you can kind of see how it converges in. So we walked down there, and walked over here. And most of you will be wondering, oh wow, why did it dive down that way and then come over? Why did it do it at an angle? And it has to do with the contours of that distribution. And I can't visualize them either, other than I can see, oh wow, there's a gradient there. That's cool. I can't see that in the function very well, but it has to do with its tail behavior, and I don't visualize tails as well as I should, but once I see things like this, now I kind of know which way the gradient is going. So it walks down there, then it gets here, it converges in phi pretty quickly, gets the variance right, and then runs to the the mean. And that's typical behavior. So you will have parameters in your distribution that mix at different rates. And they have different sizes, variances in the posterior. So the way you walk around those spaces can be tuned differently. I didn't put much effort into it, I just kind of ran everything. Here's my answer without burning anything in. So there's my distribution. I think the distribution is that, but I am no fool. I would say that looks awfully suspicious. And I would throw that stuff away. And we could verify that by running it at different starting locations and realizing this is the stationary target. I can look at the marginal distributions, but they're all messed up with the burn-in period. So when I plot the histograms of them, they don't look like anything familiar because I'm plotting a lot of stuff in the tail. So we want to chop that out. So let's do that. So I come up here, I change the burn-in period. I'm going to make it 2000. I happen to know that that's pretty good. So I would probably have to do this iteratively, rerun it at different starting points, see how we do. I left the burn-in period in this plot and my other plots, but my histograms here don't have the burn-in period in them. A lot of times I like to just see it. So I like people to show it to me. When I have students working on these things, I really like them to show it to me. So they're showing me that their code works, you know? Do it again. Show me another plot. So anyway, this is a t-distribution. I'm sorry, this is a t-distribution on mu. This is a gamma distribution. I didn't need to know that. These samples are about t-distributed. So approximately that if I plotted the QQ plot against the theoretical distribution, it looks straight. So that's basically MCMC. Let's just rerun it a little bit more. Just look at some diagnostics. I'm going to rerun it, starting from the stationary distribution so we don't have to focus on the burn-in period so much, but I want you to see that burn-in period and you always need to be aware of it. So probably just as an exercise, I need to really stress this code, make sure that this thing can really run, you know? Bam. So it's working. Probably need to work on that burn-in period because I pulled the answer so far out. And then it comes up and it converges to the right thing. So my burn-in period is extra long.
Is there any way to come up with some automatic sort of way to determine the burn-in period?
Yeah, sure, and you can do that.
Yeah, looking at error values or something.
Yeah, so intelligent systems are not too hard to conceive of. You just program up what you would do. So this sort of stuff that you do and slow yourself down, you could automate it all. So look at derivatives of this thing. Look at the trace plot when it's converged. There's little things you can do where you can bin together these points, take batches of them, and compare their means to each other. That's ANOVA. It's ANOVA, you need to do a correction on the non-IID nature of it. So that's the Brooks, Gelman, and Rubin statistic, and so people have come up with stats, things you should monitor. I get great satisfaction out of looking at trace plots, though. I like looking at them, I get your point already. What about in Heidi space? I like to look at something. So if I can't look at all the parameters, I'll look at the likelihood and watch that converge. It's got all the parameters in there, or parts of the likelihood, chunks of it. I can feed it back into that equation and look at how that's converging. Look at any statistics that I want to monitor and see how those converge. Those will be bouncing around as well. So yeah, you could. And people have written papers on it. It's almost embarrassing, right? It's like, duh. But those papers need to be written. But this thing is converged too. When we look at the non-numerically stable version, this had no hope of working. So if I take the log of this actual ratio, whole code will go berserk, it won't work. So we'll look at that next time. I want to give you back your homework, but I also want to announce I'm going to give you a quiz on Friday. And there's one thing I already know that I'm going to test you on. And if you'd like to take the remaining minute to try to guess at that, I'm open for that. Brendan. I'm going to give you a take-home midterm on Monday. We're going to do a review. Sean? We're going to do a review tomorrow evening. And a mini quiz on Friday, same nature as before. If you're here, I'll give you the answer to the quiz, make sure you know how to do it. But I just want to make sure you can do these basic principles. Monday is going to be a take-home midterm, and it's going to be open book, open notes. So I wouldn't give you a take-home midterm with like rules that I couldn't enforce. So it's going to be relatively easy study-wise, so at least know how to do one thing, and it comes straight from your homework. Jinza? No Jin. Sir? Shinri? I can do it now. Come on. Sam? Josiah? You guys know what I'm going to ask you, team?
So, right, like a pseudo code.
No. You don't know me at all. I don't see a name on this one. Does anybody recognize this? We'll come back to it. Sasha? Come on. Ishita. Jared. Juan He. June. Christiana. Zach. Ping. Who did I miss? Perfect. Quiz for 5-10 minutes. Then we'll review this code a little bit more, and I'll show you how you can really muck things up. So, talk about it a little bit more, and then it looks like I'm not going to get into Jeffrey's priors, right? I don't know if I have time to do that. I think I might have a little bit of time on Friday to do it, but I don't know that I want to exactly hold your toes to the fire on homework. I did ask you a Jeffrey's question, right? Why don't we just hold off? I'll tell you what it's all about, and we'll be able to turn that one in on homework 4. So we'll just add it to it. If you want to turn it in early, that's fine. Just turn it in homework 4 too, because we won't remember. Ask me to remind us, and I'll put it on the board so it appears in a video. So for those that weren't here, I think everybody understands. Everything good? Perfect. I might see you on Thursday. If not, enjoy the football game. Has anybody seen town ablaze on a Thursday night? Probably not, right? When would you guys have seen that? It used to be wild.